So that clock says it's time, so let's go. Really happy there's so many people in here. I wasn't expecting to fill the room. So my name is Raniz. I'm a consultant at Factor 10. And so the backstory for this talk is that I've helped a lot of companies migrate their pipelines from various systems. And I've encountered them in the wild when working with their developers and other projects. So I got the idea to make a talk about things that I've encountered that maybe isn't the best thing to do, and hopefully something you can do instead. So this is pipeline patterns and anti-patterns. Some of the things your pipeline should and should not do. So I'm going to try and work on 3 different things, try to reduce 3 different things here. And the first of them is frustration, because no one likes a frustrating pipeline. How many of you have run a pipeline? Maybe you submit your code, the automatic pipeline runs, and it fails, and the fix is to hit rerun, and then it works? Yeah? Does that make you feel good? So if we have the chance to stop that from happening, we're going to do that. We're also going to try and work on boredom, because no one wants to sit around waiting for the pipelines to finish. How many people in here have a pipeline that runs in under 15 minutes? Yeah? Depends. Yeah, that's a good answer. How many people have a pipeline that runs in more than 15 minutes? More than half an hour? Keep your hands up. More than an hour? More than a workday? Yeah, no one? I've had people who had pipelines running for more than 30 hours. So that means you have, what's that, like 3 shots a week? Otherwise, you have to retry next week. So a large focus today is going to be on reducing time, because we spend way too much time waiting for our pipelines to finish. And if we had the possibility or the opportunity, we're also going to do something for the environment. Because long-running pipelines or running pipelines doesn't necessarily have to run. Taxes are computers or servers, and running servers, well, they impact the environment more than non-running servers or idle servers. So we're going to try to keep our servers idle as much as possible, thereby saving their environment. So let's get started with anti-pattern number 1, the ritual, which is where you have a pipeline that does all the same steps all the time. Regardless of when it's run, where it's run, under what circumstances, it does the same steps all the time. So we could have maybe this pull request pipeline, because that's usually how pipelines start, right? We need a quality gate to make sure that whoever tries to get code into our code base doesn't mess it up. So we write a pull request, and we have a front end and a back end. We do some linting, we do some setup, we do tests, and then on the end we do integration tests. Works fine. But then somehow some bad changes got in, right? We can have code that doesn't work, but it doesn't result in a merge conflict. If someone changes, let's say someone renames a file somewhere, and then someone else has branched before that point, submits their code, it passes on their branch, it's merged to main, and now it doesn't compile because someone renamed the file you were using. So we run the merge after main as well. When we merge the main, we run the pipeline again to make sure that the system is still working as expected. Same pipeline runs again. And then something in the integration environment changed. Some external dependency changed, so we need to run the integration tests. We may need to make sure that they don't break over time. So these can break even if we don't change the code. So we run our pipeline nightly to make sure that we're still okay with the outside environment, everything still works as expected, and if it doesn't, we need to change to fix things. But then someone figures out that, well, our product managers, they need to run the application as well. So they need a binary, they need an artifact to run. So we publish an artifact as the last step in our pipeline. And now we have a pipeline that publishes an artifact on pull requests, after merge domain, and every night. The same binary is published every night. And this is really unnecessary. There's a lot of steps there that we don't need to do. We probably don't need to publish an artifact on every pull request, because no one's going to look at that. What you're interested in is after merge. We don't really need to run the linting, maybe, when we merge the main. And we definitely do not need to run the linting and the unit tests on nightly, because those can't change. We're only interested in the outside environment, and the outside environment shouldn't be involved in our unit tests. So what we should do instead is we should do pattern number 1, the right pipeline for the job, which is we look at each situation the pipeline runs, and we decide what should we do under these circumstances. So on a pull request, we don't publish the artifact. We run all our tests as we should. After merge the main, we run the tests, but yeah, we skip the linting because that hasn't changed. And on nightly, we only run the integration test, because that's the only thing that can actually fail on the nightly job. If your unit tests fail when your code hasn't changed, well, that's a problem, and you should fix that. But we can go one step further. We can make our pipeline smart and have conditional pipeline steps. So if we just focus on the pull request case here, on every single change, we build the backend, we build the front end, we lint the backend, we lint the front end, and we test the backend and we test the front end, right? But what if I submit, maybe I do a pure front end change. I've moved something around the front end, I changed some validation logic in a form somewhere. Don't really need to rerun my backend tests, right? Because that code hasn't changed. And the same if we do a pure backend change, maybe we add an index to a table in the database. There's no need to rerun the front-end test because that haven't changed. They shouldn't be able to fail. So we can add some logic in our pipeline to make sure that if we only do a front-end change, we don't run the back-end tests. And if we only do a back-end change, we don't run the front-end tests. We should still run the integration tests because those can still be affected, right? Because we change the back-end or the front-end, we might impact the integration test, or we probably will. Otherwise, we don't have good test coverage. So how do we achieve this? Well, I want to talk about one thing first, and it's about choices. So there's a lot of CI platforms out there. I think the most common one is GitHub. I guess GitHub is the plain coffee, black coffee, which most people use. I drink tea, so I'm probably not a GitHub user. How many people in here do use GitHub, by the way? GitHub Actions for their pipelines. How many are still on Jenkins? Yeah? How many use Azure DevOps? Quite a few. And GitLab? Yeah, a few as well. Any another platform that I haven't mentioned? Yeah, a few. Yeah? There's a few around. I'm going to show some code examples. All my examples of pipeline code is going to be for GitHub Actions, because I think that's the most common one. But that doesn't mean that all these is limited to GitHub Actions. Anything that I talk about here, you can apply to most of the platforms I've worked with when it comes to CI pipelines. So just because this is GitHub code, it doesn't mean that this is only applicable to GitHub. Of course, it won't look like this when you do it on Azure DevOps or Circle CI or GitLab or whatever you're using, but the general idea is the same, and this is just an example of the way we structure our pipeline. It's very similar with a different syntax on the other platforms. So this is how we do conditional pipelines on GitHub. So what we have here is we have an action that runs as a pre-step. We run a job before our main job, whose only task is to figure out what files have changed, and then we map them into logical modules. So in this case, we have defined a filter for the backend and a filter for the frontend. So if anything changes in the backend directory, we flag the backend module as changed, and the same for the frontend. And then we can export these from the step to the job, so they become job outputs, so we can use them. And then when our main pipeline job, we depend on the paths filter job, so it runs after it, and we can use the outputs. And then we refer the outputs. So we only did linting if the backend has changed. So now when you submit a pure frontend change, it doesn't touch any files in the backend. This will be false, so we don't run the backend lints. And we do the same for all the other tasks, figuring out when each task should run. So that's something I think you should do. It will save you time, and it will save the environment. Anti-pattern number 2, hoarding, which is if you run your pull request pipeline and you produce an artifact, you store those forever, you will have a lot of artifacts piling up. But that's not only the case, because usually, how many times have you used a 4-year-old release artifact? Probably never, right? You put them in a folder somewhere, they pile up, you never use them. Because you can probably not even deploy a 4-year-old release artifact because the system has changed. You've upgraded your hardware, you've upgraded your server, your operating systems, you've added on other servers. Maybe the database migration happened 2 years ago, so the database that release is expecting doesn't even exist anymore. So don't keep all your artifacts. In the extreme case, this leads to a pipeline failure because the disk where you store your artifact is full. And that means not only do you have to press retry, you need to go ask someone to clean out your artifacts before you can hit retry, or buy a new disk, or add more disk to your virtual server, or whatever you need to do to make more space for more artifacts. But it's also a problem of discoverability. So this is an open source project on GitHub. They have some. So this was in February this year, I think, when I took the screenshots. So over 6 years, they've published a bit over 7,200 Docker images. Now, no one's ever going to go in here and use this one, the 1.509E81C38C. No one's ever going to request that again. It's been published for 4 years. It hasn't been touched since. But if you're looking for a specific version in here, and now this might be a GitHub discoverability problem, but they all sorted like this, alphabetically, and you have to click through every page. So there's 63 pages of tagged images that you need to go through if you want to find a specifically tagged image in here. So remove your artifacts on a weekly basis or something. Delete everything that's more than a week old. You'll never touch it again. And if you want to touch it again, you can probably just rebuild it because you have the source code history for what actually built that version. Anti-pattern number 3 then, the aesthete, which is when we use natural ordering instead of practical ordering. So what I mean by that is we look at a pipeline and we tend to think that this is the natural way of running these steps. A pipeline like this, for example, we should do setup, linting, compiling, unit tests, integration tests, and end-to-end tests, where we run the whole application. We push it through the user interface in API or a web application using Playwright or Cypress. And we tend to structure things in a way like, well, we do the setup because we need to set up our tools, right? Otherwise we can't do anything. And then we do the linting step because that's kind of cheap, and we need to lint our code before we compile it. That makes sense. And then we compile it because there's a requirement for running the code. Then we run the unit tests, and then we run the integration tests, and then we run the end-to-end tests. But if something fails, and in my projects it tends to be the integration tests or the end-to-end tests that fail first, because I do test-driven development, so my unit tests, I usually don't commit before I make sure all my unit tests pass, but maybe sometimes I forget to run the integration tests, because that's not always part of my development flow. But in this case, the integration tests fail. That happens after 13 minutes, almost 14 minutes. But if we look at this and we figure out that, well, in 70% of a pipeline failure, it's the integration tests. It makes sense to run the integration tests as early as possible. So if we structure it like this instead, we do the setup, we do the compilation, we need to compile before we can run the integration tests, and then we run the integration tests. We saved 4 minutes before we figure out that our pipeline has failed. And if everything passes, it's still the same amount of time before we get to that green check mark. But if the integration tests fail or the end-to-end test fails, they fail earlier, and we get that feedback earlier, so we don't have to sit around waiting. This might mean that we don't need to context switch, which saves us a lot of time in the long run. Anti-pattern number 4, the one pipeline. One pipeline to rule them all, one pipeline to bind them. And this is where you have just one pipeline. One long pipeline that does everything for you. We have backend setup, backend linting, backend compile, backend tests, and the same for frontend. And then we're on the integration tests at the end. Quite a natural way of doing things. But if we look at some timings, so this is timings from an actual project. I took the crates.rs, so that's the dependency manager for Rust, where all the public dependencies, the dependency repository are stored. So this is the source code for that. I didn't take their pipelines, I wrote my own, because they do some things that I didn't want to have. The timing diagram got quite cluttered. So this is setting up Rust, running the Rust linter, compiling in Rust, running the Rust tests, and then doing Node.js initialization, linting with, I think, ESLint, compiling, and then running the tests, and then running integration tests, which I think are done with Cypress. So that's probably more end-to-end tests. But this takes almost 25 minutes to run. And you're definitely context switching here. You're submitting your pull request, you're waiting. You can't do anything before the pipeline passes, right? Because you don't want to tell anyone, hey, please review my code until you know it actually completes the pipeline. So you need to wait 25 minutes. And then you go on and you do something else. And then you remember, oh, wait, I had that pipeline. I started that 4 hours ago. And you switch back. So you get these constant interruptions in your flow. So what we should do instead is that we should split this up into parallel pipelines. In this case, we have one backend pipeline, we have one front-end pipeline, and we have one integration test pipeline, because that needs both the front-end and the backend. So we do backend setup, linting, compiling, and tests in one pipeline. And then we do the same for the front-end in another pipeline. And in the third pipeline, we just compile the front-end and backend so we can run the integration tests. And this means that instead of 25 minutes, we're down to slightly less than 15 minutes. Still a long time, but maybe not enough to force that context switch. We saved almost 10 minutes on the total time before we get the green check mark. But we have, since we do the compilation twice, added on 8 minutes of total runtime, which means that we are actually, this is worse for the environment. But we can fix that. So we can make the integration tests rely on the backend and front-end pipeline. So instead of just ending them, we publish a temporary artifact. We shouldn't store these. A pipeline artifact. And then we make the integration tests depend on the front-end and backend pipelines. And we use the artifact in the integration tests to run the integration tests. This means we only do the compilation once for both backend and front-end. And this is as another minute to runtime. But the total is the same as for the original pipeline. But we can do this even better. So if we split this into 5 pipelines, it looks like this. So we have a backend setup with compilation, and then we publish the artifact. And we should do the same for frontend. And then we start 3 new pipelines. One that runs the integration tests, and then one that does the linting and testing for both frontend and backend. And now we're down to 12 minutes before we get that green check mark. And the total running time is the same as for the original single one pipeline. There might be some more, because there's probably delays involved and you need to upload and download artifacts. But in the bigger picture, it doesn't really matter that much. You get quicker feedback, and you don't have to sit around waiting. It's efficient. Now, there's a limit to how much you can do this depending on what kind of setup you have. If you're running on-premises, you just have a limited amount of build servers. In extreme cases, you only have the one build server, and you're out of luck. This won't work, because regardless of how many parallel pipelines you have, if you only have one executor, you have a serial pipeline. But if you're running on something like a cloud, GitHub Actions, Azure DevOps in the cloud, GitLab, CI in their cloud, you have essentially infinite parallelability. So you can split it up as much as you want. Take a look at your pipeline, identify what you can run in parallel, and try to optimize it. Use artifacts intelligently, but be sure to remove them when your pipeline's done. And we get to anti-pattern number 5, which is gift wrapping, where we use wrapper tasks to execute our command line tools for us. I'll go into the history behind this shortly. But say we have something like this. So this is a fictitious action on GitHub Actions that runs cargo for you. It looks kind of nice, right? We write some YAML, we tell it what commands we need, we can tell it the arguments. We want to run the release target for the whole workspace with all the features, right? Nice, but we shouldn't do this. Why? Because maybe we want to do something that isn't supported by this action. Someone wrote this action, it's stored in a GitHub repository somewhere, and you're limited to what they support. So if there's a new release, maybe you can control the parallelization of the compiler by adding on the jobs argument. But this action doesn't support that. Maybe it has an escape hatch where you can use, like this, you can just tag on any arguments you want to, and it will add them at the end. But if you're unlucky, you have to wait for someone to make a new release of the tool you're using. Maybe you need to make a pull request to get that in, or you need to fork it because the maintainer got bored. He only did this, and then he has abandoned the project for the past 6 months. So what you should do instead is you should just call your command line application directly with the switches. And if you use YAML multiline formatting, which is, by the way, its own website because it's so complicated, you can structure it like this. And I think it kind of looks quite neat as well. And the bonus here is that there's no argument that is unsupported. If the order matters between arguments, you have full control over that. And there's no hidden magic. So what prompted this in the beginning was that we used, I was at a client, they used the .NET task in Azure DevOps. And we had some problems because we wanted to manipulate the artifacts. But the tool, when you used it to publish artifacts, didn't store the artifacts in the location where it was expected. It did some hidden magic, which was in the task, and it added on a few command line arguments to the .NET binary, which we didn't want there. Because the developers behind the task, they thought that this was something that everyone wanted, but we didn't. So we switched to just calling the .NET binary manually, and everything started working. So I'm not saying don't use tasks. I'm just saying don't use wrapper tasks. So in this case, you should definitely use things like setup tasks, which installs specific versions of your tools. And in this case, this pipeline runs Python. It uses a setup Python task to get a specific Python version. And then it uses a poetry task to get a poetry, which is a build tool for Python. And then we run the build tool as a command line tool. Works much better, so we use the tasks for what they're good at. We're on to anti-pattern number 6. It's complicated. And this is where the pipeline is its own software project. I was with a company, I think they actually had their own bug tracker for the pipeline. And their pipeline, all their pipelines in all their projects basically look like this. So this is Jenkins, where you write your pipeline, it's Groovy code. You can publish that as a jar file. You upload it to Jenkins, and you tell it that this is version 4.3 of my pipeline library. And you can include it in your pipeline, and you can just call pipeline. Done. But how do you change this? Well, you need to fork the repository. You need to make some change. You need to publish a new version. You need to upload it to Jenkins. You need to specify the new version, which is, in this case, maybe 4.4. But maybe I'm not ready to publish it yet. So it's probably like 4.4 alpha 1. and then I need to point that out in my pipeline, and then I can run my changes. And if they don't work, I need to do all that again. And they also even had some configuration in their XML file that controlled what this pipeline, which is actually just an application at this point, did. So what should you do instead? Well, I think you should do, because I like the reusability of this, right? They had probably like 30 projects that had basically the same pipeline. But in all the cases where they differed, they had a bunch of escape hatches or control flow. So there was a lot of if statements or whole parts that were just different parts of this, this huge library. So I'm a big fan of composable pipeline libraries, which is pattern number 5. So we're back to GitHub again. So this might be a Rust pipeline where we use actions. Or it actually shows. So we use the GitHub action for checkout. And then we have our own pipeline actions here, which is reusable, where we can just compose our pipeline. We have a compile Rust action, which does the things that we generally do when we compile our Rust applications. We have a test, which might run things as coverage and prepare reports and upload them to the correct place. And we have a publish artifact, which maybe publishes them to our common artifact server. And we can use arguments to change how it works. So in this case, we want to point out which specific artifact it should publish. And we can go one step further. We can take, because this is steps, right? You compose your pipeline from steps. But if all of the pipelines look essentially like this, you can go one step further and you can make a reusable pipeline library. And this is where you just include your pipeline. You have a predefined pipeline, you say, I'm going to use this pipeline. Now, isn't this really the anti-pattern for complicated? Not really, because this is composable. If you want to break this if you're using this pipeline and you want to break it up, you can go back here and you can insert your own steps in the middle. So it's very easy to switch back and forth, and if you want to modify it, you can just copy it and make your changes. You can do a company-wide library of these things, where projects can use your standard pipeline, but they can also go do things that they want to do that differ from the standard pipeline, while still reusing all of these actions, so they don't have to do everything from scratch. And this is very much related, so this is why it's pattern 6.5, entangled, which is when you're entangled yourself so much into your pipeline code that it's hard to get out of there. The Jenkins project, the pipeline project, was around 4,000 or 5,000 lines of code. It's really hard to port when you might want to migrate out of Jenkins, which is what I was there to help them with. So what you should do is you shouldn't put all your build logic into whatever your build system is using. Try to make use as few features of your build system as possible and put your stuff elsewhere, which is pattern number 6, when you script your pipeline. So this is a Python pipeline again. We see setup Python, we see setup poetry, but instead of calling poetry and making complex stuff in our pipeline, we use make. So make is an extremely old build tool. It's generally used for C, maybe even C++ projects. It's been around for ages. But it's essentially just, probably it's the first build tool, or one of the first build tools. You tell it to run something, and it runs shellcode. So we use that to hide all our complex logic from the pipeline. So we then have a make file that define all these. Now this is a very simple pipeline, but you can have things that depend on other things here. So that you can see here, we have test, type check, format, style check, lint, and init. So init, which is what we do first, we initialize the project, we install all the dependencies and all that. Then we just run make CI. And then make figures out that, well, CI, they require us to run style check, lint, type check, and test. So it runs those in that order. And the main benefit of this is that if I want to do something complex and I want to debug it, I can do that from my command line on my laptop. I can run make CI on my laptop and get the same results as I do in the pipeline. If I define all of these as jobs in the pipeline, there's no way for me to run that locally. There are build tools that can do that, but most of them, and especially all of the popular ones, can't run locally. There is a project to try and make GitHub Actions run locally, but I've never gotten it working. GitLab had support for running your pipelines locally. You can run the GitLab runner locally, but they have deprecated that. They're not supporting that anymore. And I'm not aware of any way of running Azure DevOps pipelines locally at all. So put your complex logic into scripts. We had a situation where we had quite a complex setup for an integration test. And we put that into a PowerShell script. And then we ran the PowerShell script from Azure DevOps, which meant that instead of iterating, changing the pipeline, pushing the pipeline, waiting for it to run, we could iterate locally. We can run the script, see if it worked, change the script, rerun the script. Much, much quicker feedback loop and less waiting around for servers to start. Or even there might be build queues in your system, so you need to wait for other people's pipelines to run before you can test your latest changes. Moving on to anti-pattern number 7, Groundhog Day. And if you don't get the reference, it's a movie, and you should probably watch it. So Groundhog Day is when we start from scratch all the time. This is very common now. It wasn't before. Back in the day when we used Jenkins, some of you still do, we didn't start from scratch every time. Like in the beginning, Jenkins checked out your source code, and then when changes came, it just checked out the new changes on top of what was already there. It kept all your builds, all that, in a workspace. It still does it if you don't tell it to clean before. But you usually tell it to clean before, because keeping all these around can cause issues, which is why it was introduced. But nowadays, usually we get a fresh instance, actually, often it's a new virtual machine, completely fresh. We install our stuff, we download our code, and then we compile and test it. Everything is done all the time from scratch, right? Checked out clean, nothing is there. We download all the dependencies. The dependencies are even cached in our local directory. We need to fetch them from the internet and down, right? It takes some time. This is just for the Rust part of the pipeline I showed earlier, the crates.io. It takes 12 minutes for the backend. Fetching, linting, compiling, and testing. So what we do then is we cache pattern number 7. How many people in here have caching in their? All right. I'll just do it without. All right. Okay, I'll do the mic then. All right, so caching your dependencies. The idea is that instead of going out to the internet all the time, fetching all our dependencies every time, we store them locally on a server closer to our build servers, and we fetch them from there. So we do a restore cache, fetch dependencies, and then we might need to update the cache after we fetched all the dependencies. The thing with this is, fetching dependencies is kind of quick. In this case, fetching them from crates.io directly takes 7 seconds. Fetching them from the cache server takes 4 seconds. And then we need to make sure that we have all the dependencies there, and we might need to update the cache. So in total, we're going from 7 seconds to about 5 seconds. That's not really worth it. It might be worth it for different reasons, which is that this does not rely on your internet connection. If you have a flaky internet connection in your on-premises,
this might be more efficient. You definitely get less variability in this, but overall, you don't save much on this. So there is more interesting stuff we can do. We can cache build output. And this is what we used to do with Jenkins. We kept the build output around, so next time we just check out the changes, and we just rebuilt whatever has changed. But now when we start from scratch, the previous build output isn't there. But what we can do is we can put that in the cache instead. We can put the dependencies in there as well. We get them for free. But if we cache the build output, so we do restore cache, and then we do linting, compiling, tests, and then we update the cache. So if we look at timings, the original, starting from scratch, takes 11 minutes. Restoring the cache takes around 30 seconds. Linting goes from 2 minutes, 29 seconds to 24 seconds, because it only lints the new changes. Compiling goes from 5.5 minutes to 2.5 minutes. And then testing obviously takes the same amount of time, because we need to run all the tests all the time. We can't cache those. And then we update the cache if necessary. So we saved almost 5 minutes, 4.5 minutes, by just caching 2 gigabytes of data on a server somewhere. This is really efficient. Depending on what your build process is, this might not work. This only works for incrementally compiled languages, such as Rust, C, C++, C#, I think. It won't work for TypeScript, because TypeScript is compiled from scratch all the time, regardless if you have something lying around from the last time or not. It won't work for CSS compilation and things like that. Depends on what language you're using. And some of the build tools have more or less support for this. I know there's a lot of work in the Gradle community for Java, for example, to get this working on CI. And if once we've done this, a lot of our pipelines nowadays result in a container image. So we can use sort of the same idea for container images. If you've ever tried caching container images, you will notice that it takes a long time if you do it manually. If you export an image, upload it to a cache server, download it, and then import it, it takes a lot of time. But what we can do is we can let Docker do the caching for us. Now, Docker can't do it directly, but if you use BuildKit for Docker, you can. So what we do is we use BuildX, which invokes BuildKit, and then we tell it to use a cache, and we tell it to cache to and cache from. And this needs to be a separate image. This can't be the same image as the one we're building, because it's different information. So I typically just tack on a suffix called cache. And what it does now is that when it goes to build your image, it checks in the cache. Have I done this before? And if so, it downloads that step. It's like building locally when you build from Dockerfile. If you only change one row at the end, it will reuse all the other steps and then just do the thing at the end. This is the same with a remote cache. So if we build an image, in this case, we install 2 tools with cargo. And you can see here, it's importing the cache manifest, and then when we come up here to step 3, it should run cargo install, and then this. But you can see here, it found this in the cache, so it only took 8 seconds. Now, if you actually go and install Leptos, in this case, it takes around 6 minutes. So this saved us almost 6 minutes of time. And then we get to the end here, which we have changed some version of cross. So now it actually needs to do that. And that takes 6 minutes. But we saved 6 minutes from the previous step. You can see here that it found it in the cache, and then it does this. And we can use this to do pattern number 8, which is tooling images. Which is, instead of starting from scratch, if you need to install some tools, bundle them into an image. So what we do is we add a step at the beginning, just as we did with the pre-check step that checked if something has changed. We do a step at the beginning which builds our tooling image, and then we run the steps after that on this tooling image. So in this case, we built the image, call it tooling, and when we tell these to run on that image. And we only need to do this. We can combine this with the conditional logic. So if we haven't changed anything in the build image, we use the latest version from our main bash, for example. So in this case, we had an index on user birth dates. We haven't changed the build image, so we use the one from the previous run, or the latest from main. And we run our tests and our compilation on that. But then a change comes around that builds the image, that changes the image. Then we need to build the image, we publish it as a new image, and we use that image to build the pipeline, to build that change request. And once this has passed and been merged, we do everything again on main, which means that we build the image and we publish it to latest. So now everything that comes around after that is using the new version of this image. If you do this, you need to be pretty careful so you don't run into anti-pattern number 8, interference, which is where we collide with other pipelines. And there is a huge opportunity to do this when you're doing build images. If, for example, you're using a shared repository and you always publish as latest. So in this case, we have built the image, we run our front-end and back-end pipelines. But while we're doing that, another pipeline comes around, starts up, builds the image, publishes it to latest, which is the same image we're using here. So what happens now? Well, when the backend and frontend steps pass and the integration tests run, they run on this image because it's been published and then it's pulled from there. So there's a high chance they fail because something has changed in the build environment. These will of course pass because they're using the image intended for them to run on. So what we should do here is we should use an identifier that's unique when we publish our tooling image. And in most of cases, that's the git commit SHA, because that's pretty much guaranteed to be unique between all your pipeline runs that you ever will do. There's also a high chance of doing this if you're using shared resources for, say, let's say, a database that you run your test against. If you run all your tests against the same hard-coded database name, there's a high chance you will get conflicts when two test suites run at the same time. So, anti-pattern number 9, overloading, which is when you run on underpowered machines. Please don't run your pipelines on Raspberry Pis. But I see a lot of this because for some reason people are pretty cheap with their CI hardware. So I've made a few rules of thumb for build agent sizing. So number 1, the build agent should be at least as powerful as the least powerful developer machine. Which means that if all your developers can run the code, if you make sure that your build servers have at least the same amount of memory available and at least as many processors, they should pass. And number 2, ideally, the build agent should be at least as powerful as the most powerful developer machine. Maybe this isn't practical because some people buy laptops with 250 gigabytes of RAM. But if possible, make sure that your build agents have more power available than your developers, because in that case, hopefully, the pipeline runs faster there than on their machines. And they will be happy running their pipelines because it's quicker than running them locally. And if the build fails because of lack of resources, beef up the build agent. It's the quickest and probably cheapest way of fixing your pipelines if they run out of resources. Instead of spending 3 days trying to reduce the memory footprint of running SQL Server in a container, just give it more RAM. It will work. And if the available build configurations aren't sufficient, consider at least rolling your own. So, should you run your own build agents? Well, there's a few pros and cons on this. Compared to using cloud-operated ones from GitHub, GitLab, Microsoft. So the first pro is you get full control. You can control what versions of operating systems, you can control what hardware there is, you can control all the specs, but you need to maintain them. You need to make sure you update the version of the software running your pipelines, whatever calls home to your pipeline platform. You need to make sure to upgrade your operating systems. I've worked with build servers that were on, I think they were still on Red Hat 6, which was 8 years out of updates at the time, I think. That's not good. I think the last project I was on had Windows Server 2012. You get right sizing, which is that if you need 6 gigabytes of RAM, you can give them 6 gigabytes of RAM. Typically, when you run on cloud, you either get no choices, or you get choices which doubles all the time. You get 2, 4, 8, 16 gigabytes of RAM. If you need 9, you can get 9. But you need to manage scaling yourself. And this can be a problem if you want to parallelize your pipelines, or if you have multiple teams using the same build servers. You need to make sure that you reduce the queues by having some sort of scaling mechanic. The scaling mechanic can actually be just having 20 servers which are idle because that's your peak. But if you run in some sort of cloud, you can probably use some sort of auto-scaling to make sure that there is enough servers for the workload that's happening at the moment. Or some prediction where you know that after lunch everyone comes back and they run their pipelines. So we scale up by 50% at 12:30. Someone needs to manage that. And cost, can both be a positive and a negative, right? So if we compare with, I've taken figures for GitHub Actions and GitLab. So on GitHub Actions, you pay slightly less than €1 for each build hour you use. On GitLab, you pay slightly more than €1 for each build hour you use. If you rent a cloud server, you pay around 10 cents for an hour. So it's 10 times more expensive to run your stuff on GitHub Actions or GitLab CI than it is to run on your own servers. If you rent them in the cloud. If you have your on-premises servers, it gets much, much cheaper. But someone needs to maintain them, and maintenance costs. If you already have an internal IT department that is happy to run your servers for you, the added cost probably isn't that high. But if you need to have your developers run and maintain your servers, or you need to set up a new department for it, cost is probably very high. So, what's next in the area of CI pipelines? There is 2 tools that I've been watching and I want to play more with. I haven't used them in a real project yet, but it's Dagger and it's Earthly. So both of these are built on the same ideas as our tooling images when we use the Docker cache. They're built on BuildKit, which means they use the exact same caching mechanism as when you build Docker images. So if your source code hasn't changed, the compilation step is just cached. It uses the previous results from compiling, and then it continues on with the same step. So if in the conditional pipeline case, if your backend hasn't changed, the backend pipeline will use cached results. And then you get the integration tests, and it will use the results from that. So you get the conditional logic for free. Dagger uses programming languages, and I think introducing programming languages into pipelines is a bit dangerous, because when you give programmers a programming language, they tend to write software. And we don't want software in our pipelines. Earthly uses a blend of Makefiles and Docker files, which looks kind of weird but works pretty well. There is a lot less room for making complex software in those files, and it encourages you to call out the scripts and other things, which I would recommend. But I haven't played around with them enough yet to know if they're actually the future. So, quick recap. Don't do all the things all the time. Don't hoard all your artifacts, delete them regularly. Don't order things in a way that makes it look good. Order them in the way it makes most sense and reduces the feedback time for you. Don't have just one pipeline. Make sure you parallelize when you can. Don't use wrapper tasks. Make sure you know your tools and use them as they're intended. Don't write complex software in your pipelines. Just have complex software in your software. Don't do everything from scratch all the time. don't break other parallelly running pipelines, and don't run your builds on Raspberry Pis. All right, that's pipeline patterns and anti-patterns. Thank you. I think we have time for some questions. If
I would like to say thank you for a talk and give some small presents.
thank you.
Thank you so much.
Thank you. The QR code up there leads to my LinkedIn. I promise it's not malware. So if you want to connect with me, scan the QR code. And how do we do questions? Should you just shout, or should we pass the mic around? Yeah? Then you won't hear the answers on the stream.